So I was asked to prepare a little how-to to create an equation to calculate intensities based off of a location, starting with the NOAA Atlas 14 data. And so I pulled up NOAA, this is the NOAA Atlas 14, you just Google it, I'll bring you to this. And so this gives you, I guess I would relate it more to the IDF curves in the past, since we've been using the past. This is a little more geographically accurate stuff. So we're in Indiana, so we'll find our data through here, and we're working on a site in northern Indiana by Goshen, and we'll find it. Here's Goshen, and we'll zoom in a little bit more. It took me a while to find the zoom in button. But here's site. We can kind of pick anywhere in here. Not sure how big a variability there is off of it. We are working on this swiveling ditch through that, and I don't want precipitation depth, I want precipitation intensity through that. And now pick my site there. I just double clicked and it gave me my site right from that, and that looks like it's in a good spot. You can move it around if you don't like it. Down here is the tabular data for this, and you can see for a 5-minute duration, a 1-year return period, and then it's a 4.26 inches per hour through that. And this is, I guess, 90% confidence through that, and that's great. You can see it if you want to see the curves. Here's the curves for it at this location through that. We're going to stick with tabular data, and I'm going to download that through here. And do I want to do this estimates table in CSV format? Yes, of course I do. Yep. And just going to do that one is all I need. So click submit. It pops up now. Let me open this up. And I got this on a different screen, so I'll scroll this in here. Here we go. Let me squeeze this in to fit. There we go. All right, through that. So this is the data downloaded from it, and here's the data, and that should be exactly what we saw here. Here's the 4.26, 5.11, 6.16, so forth, and so on, right through that. And yep, 5.11, 6.16, yep, so that's it. So this is giving us the data, and how we normally do it is we calculate a time of concentration. We want to know what's the intensity during the time of concentration, which will, as you know, give you the highest flow rate for whatever your watershed is. And maybe it's you're looking at a 10-year storm or a 50-year storm or a 100-year storm, and then your time of concentration is almost never right on the nose of one of these pre-selected durations, and so you're going to work through the you have to do interpolation or pick the higher value. Some people just do that. You probably like a 47-minute duration, and that's, where are we? We're almost halfway between 30 and 60. And if we're looking at a 50-year storm, we're going between 2.6 and 3.95. And you can do linear interpolation. That's what we often do in class, but that's not that super accurate in there because it's a nonlinear problem through that. If they were smaller intervals, it's probably not that big of a problem, although it gets less linear toward the shorter duration ones. So that's the issue. And what we want to do is we want to be able to write an equation that we can just type it in, whatever our time is, and it calculates what the intensity is. And the original Indiana Stormwater Drainage Manual had tables in it, and that's what actually the Elkhart County standards are still from through that. And I'll slide over another spreadsheet I had for that. Here's an example of IDF table that was in the original standards for that. And if you look at the Indiana Stormwater Drainage Manual, I think 2015 was the last edition they had from there. They give you all these values, and this is our closest station is South Bend. They have South Bend, Fort Wayne, Indianapolis, Evansville. Through that, so our closest station is South Bend, and the equation for intensity is this, right through there. So you can just plug in any of these values. T sub r is your return period, And so if you plug in your return period and your time, and this one's in hours, it gives you an intensity, right, through that. So a 2-hour intensity 10-year return period, if you look over here, oh, it's 1.01, and that's what that is. And so it worked. Right, through that. So that's what we've been doing before. And because each watershed you do, and in a big project, you have a lot of watersheds that you're trying to calculate for every storm drain crossing or culvert crossing, you have to have a new watershed. And they all have, random times of concentrations that never line up exactly on these duration figures. And so in this way, instead of doing a bunch of interpolation, you just plug it in and you get your number. So that's what we wanted to get back to. We wanted to get back to being able to do that. And reading through the reports from NOAA Atlas 14 and how it's done, and it's geographical, and they're doing a lot of geographical interpolation from NOAA's gauge points and things like that. And so there's a lot going on. And in the end, they basically just said, yeah, we don't provide those coefficients anymore like we used to, or in the old days, with the I equals, whatever. And just Googling it says, well, we can just use a polynomial to figure it out and calculate it through there. And so we can do a polynomial curve fit off of this data. And so that's what after this long preamble, that's what this video is really about, is how to calculate, how to do that, right? How to calculate, do a curve fit to recreate these numbers using an equation so that I can just plug in any old time for my duration or a time of concentration and calculate an intensity. And then also for whatever return period we happen to have through that. And so I just did this at the office this morning. Well, started yesterday and finished it this morning through that. So while it's still fresh, we're going to do this video so we don't forget how to do it next time we need to do it. So I'm going to make a new tab here in my spreadsheet, and I'm going to pull data out. And for each return period, I have to do a new curve fit for it to make it match. In the old days, then the older version of this, usually they broke down something less than 60 minutes versus something greater than 60 minutes to do a better job fitting it. There's different values for that. We're just going to do a single polynomial curve fit, but it'll be a third degree polynomial, so it's a pretty good fit. We'll see in a second here through that. The way I've broken it up through here, and let me find my other spreadsheet. Just downloaded through that. There we go. Through here, and we're going to split this data off, and what we're going to end up with is let me find that equation. All right, I'll show you how we get here, but I want to show you the equation first before we move too far into it. This is for the curve fitting. This is the polynomial that we're fitting, and it's the log of the intensity is equal to some constant coefficient a or y-intercept times b times the log of the time, and t is in minutes in this case, plus c times the log of t squared plus d times the log of t to the cubed power. All right, and actually I'm going to make this bigger so you can see it easier. So this is the equation we're trying to solve, and we're going to do a regression analysis using Excel to figure it out. And I didn't know how to do this until yesterday. You can Google it and learn the same way I did it through that. And in the end, we're going to end up with values for these coefficients based on the different return periods right through that. And I just pulled down a new clean set of data, so we're going to start working through that. And that's our summary. And we start off with here. And this is, you can see the curve fit here, and you can fit a curve and write the equation on it. That's one way to do it. Or you can use the solver and the data solver tool inside Excel, and it'll give you the graphical version of it. And the graphical version looks like this when you're done. And then here's your coefficients. And that's what and I'll show you how to do that. Only on the first one did I do the plot, because plots look cool. That's one way to solve it. From there on, I just did tabular to get that through there. So what we're trying to fit together though is this equation. So I need the log of the intensity is equal to some polynomial, and the x variable in this polynomial is the natural log of the time. And so being that type of curve we've got, it's a natural log to natural log kind of a relationship, right, through that. And so that's what we're fitting the plot through. It does seem to work really well. Why do we need to use natural log? Because Google said so. Someone smarter than us figured it out, our AI overlords, through that. So that's what we're going to start off with. And so the first thing we're going to do, if we're making a new spreadsheet here, and so let's do one for the 10-year storm. So we'll do 10-year storm, and we'll start off, we always have duration, and the duration from the table here, and I've never gone more than 24 hours, but they like to list a lot. So, right, they've got 5 minutes through 24 hours, right? I'm just gonna convert all of that to start with into minutes, and if you trust me on that one, here's the minutes right through there. So there's my duration in minutes through that, and so 5 minutes, 10 minutes, yeah, an hour, 2 hours. That's how they're jumping through here, and then you finally get to 24 hours, which is 1,400 minutes right through that. So that's my minutes. I'll make this a little bigger so we can follow along easier at home. Right, through there, so there's my minutes, but I need the natural log of that time right through that. So there's my natural log of t, actually, yeah. And so a natural log of t then is the equation in Excel is just ln, and then whatever value you've got, and there it is. Pull that down, and now we've got all our values here, and that never changes for any of the setups we do right through that. The next thing is what's my intensity, and again, and this is the 10-year storm I'm looking at, so I'll put that up here so I don't forget. That's what I'm doing. I need my intensity, and I come back to this table. What's my intensity? And I need from 5 minutes down to 1 full day, and I'm just going to do Control C, copy that, drop it over here, paste it in, Control V, and double check, make sure it came over fine. Yep, 0.159, 6.97. All right, looks great. So that's my intensity, and do inches per hour so we don't forget. That's what we're basing this all on. All right, through that, and now I need to find the natural log of my intensity. Through that, this is an I. I know it looks like an L, but it's really an I. Name the font for that, and same idea. This is just natural log of that. And pull it down, and we'll get some negative numbers once you drop below 1 through that. And right, that looks good through there. And I've done this before, so I'm double checking. Yes, we are in good shape on that. All right, through that. And then the next thing that we need to know is, right, if we're gonna, let me copy this equation and put it up here at the top so we don't forget it. All right. This is the equation we're trying to solve, right, through that. And you can say log of t is x, right? And log of t squared is, or log of t squared is x squared or x cubed, right, through that. And so we need to calculate these coefficients from these, and so you can call this x squared, x cubed, and then each one has a coefficient plus some y-intercept or some standard coefficient out in front, a. We're calling it a in this case. And so I need to find out x. I need to find out x squared. I need to find out x cubed. And so I'm just going to draw those, or type those in like that. Right through there. I don't know what those are. I'm just going to plug in a bunch of ones right now for this. Why not? They're all ones right through there. And now we should be ready to use regression. And in linear regression, and we should have saved this earlier, and we're going to have to do a save as, Browse, and I'm just going to put it on my desktop for now. Not a great place to put it. And I don't want it as a CSV anymore because I wanted to keep all the formatting and stuff we're going to do. So we're going to make it into an Excel sheet. And usually I do this first thing when I download a CSV because otherwise you try to save it all of a sudden and it won't save because it can't do formulas as a CSV. So now it's an Excel sheet. And so that's what we should have done. Start with, so now we've got that ready to go. You got to make sure you have under data tab, you have to make sure you have data analysis and that you have down here regression on that. If you don't, you need to come over here to File, Options at the very bottom, do add-ins, and you need to manage your Excel add-ins. So down here, this will tell you if you already have it loaded, but you can go to manage it, and you've got to turn on analysis toolbox and solver as well. And if you like Visual Basic, you can plug that one in. And just got to make sure those are all turned on. If they weren't, if you didn't already have it and it doesn't come standard, that doesn't come turned on by default. So if you turn it on, it'll load and then you'll have it. And so once that's loaded, then you come to data. You wouldn't have had this analyze tab here on the ribbon before. Now you do. You hit data analysis, scroll down to you see regression and click OK. And so now regression is saying, well, to get some Y value, some output, what do I need to change to get there? And so my Y output is my log of my intensity. It's this, right? This is the Y side of the equation. So there's my log of my intensities. That. And what can I change to get those numbers? Well, I am going to change. I'm going to change all of these values to get that. And it'll do a new worksheet, or you can put it in a worksheet you've got from there. I usually do a new worksheet, but we'll see. You can say it has to pass through 0. I don't do that. If you were to cover if you were to highlight and grab the headers, labels at the top of each column, you can click that and it knows that you did that. But I'm not going to do that. So we're going to try this out. And we didn't get good numbers. That should have worked. Let me find out why. Okay, I figured out why. These x's, I actually have to put numbers in there. I can't. So the x by itself is just log of t, right? X squared is this one to the second power. If I had actually just read my labels, I would have known. And then this one is to the third power, right through that. And now we've got those. I'm going to bring those through. Got that. I'm going to get rid of this sheet because I screwed that one up. All right. Now we're going to do it. Now we go back. Oh, good practice. See? Now we're going to go back to data analysis, regression. Okay. Remember some of these things for us, right? Yep. So my y values are my natural log of I, and my x values are these guys. And all that's good. And it pops out. And here we go. Let me make this bigger so you can read it. And there's my regression analysis. And I'll make these a little bit bigger. So there's my intercept values. And here's my coefficients. And these coefficients are the A, B, C, and D from this equation. Right. So now we have all those values through that. And let me double check, make sure these values are correct. Yeah, they are. All right, so we did a good job through that. So now we've solved it. We can make it work now with these coefficients based off of that. And sorry. And so now how do you use this? All right, through that, well, if we copy these coefficients, right, from here, let's go back over to this page. for that. And I'm going to drop these coefficients in here, and I'm going to remind myself what they are. B, C, oops, come on. B, C, D, that's those guys from, from this equation, right, through that. And so now if we wanted to code this, right, and so I've got a t here, and my t is some minutes. And this is set up to be in minutes. And so, so if I have my t, and this is again for a 10-year storm only, it only works for a 10-year storm, so there's my t is in 10 minutes. What's my natural log of t is going to be equal to the log of that. Make a more interesting number later. We've already had that number. So there's my natural log of t. And now I can calculate all of this. And what I'm calculating is the natural log of I. So we don't forget, let's label that natural log of I. Then it doesn't look very good, does it? Through there, and that is going to be equal to all of this. And so it's going to be equal to A plus B times the log of T plus C times the log of T squared plus times the log of t to the third power. So all right, so that's the natural log of the intensity, and I want the intensity, and so to get the intensity, center all these things. To get the intensity, I need to raise that to the e power. I need to raise this to the e power, and the equation in Excel is exponential to that guy. There we go. So if I did this right, at 10 minutes, my intensity should be 5.38, and I got 5.41. Well, in my world, that's plenty good. All right, through that. And so we can do a bunch of different times, right? So now if I need to know 8 minutes, there's my 8-minute value, right? If I had 7 minutes, there's that. Right, and in lower numbers, you're going to have less accuracies, but let's try 35 minutes. Oh, okay, let's check a couple of these, right? Here's 30 minutes. What does 30 give us? 30 is 3.03, 30 minutes, 3.07. We're off by 400ths. Sounds fine to me. Here's at 60 minutes. My intensity is 1.92, 1.95. We're off by 300ths. Sounds fine. All right, see, there's so many other variables that are probably wrong in these calculations, especially if you use the ever-loving rational method. Then this is the least of my worries. Through that. And so why we want to do this is because we usually have like 47 minutes. And instead of having to do interpolation here, I have directly calculated, and that's going to be a lot more accurate than any of my interpolation through that. So that's the setup. That's how you do it. You'd have to do it again for every return period, and you'll have a whole different set of coefficients for each one. And again, here's the spreadsheet I worked on earlier with this, and I'll squeeze that in there. Through that, and this is my summary sheet, and in the end, right, here's all my coefficients for each of these different return periods. I've got this set up over here that it does a horizontal lookup, that if you set what your return period is here, like I want to do a 100-year storm at 47 minutes, it'd be 3.28. If I wanted to do, 78 minutes, right, it'd be that. 50-year storm, 10-year storm, but it has to be one of these set values because it's doing the lookup through there. I can't do a 12-year storm. It'll still read 10 because that's the last number it found in there, the closest one to it. And so it only changes. We want to do 1-year storm, right, through that. And that's why we want to do this, is so that it makes our life easy. We don't have to do all these table interpolations and lookups from that. And so we got that value. I went through and did some accuracy checks. I was curious and to see how good this was off of some data I had earlier today, which is apparently very similar location as I picked this time through that. And so here's my calculation using this polynomial curve fitting piece. Here's what the actual value was from the NOAA Atlas. All right, from that, here's my error value in it. So at a 5-minute interval, I'm off by 0.025 inches per hour, and so forth and so on. You can see the longer the period, this is a 24-hour one, we get much closer. And that's a 1-year one. Here's 10-year error calculation, right? That's the one we were just looking at. I started off at 0.04 off, and then it gets a much, much better fit as we go along. Here's the 100-year one, right through that. So I guess you have to answer for yourself whether you think that's close enough. If if you don't like it, add a fourth term on here. Go to a fourth order polynomial. Add a A B C D E to the fourth power out here if you wanted to be even more accurate from that. Or you could split it up into from 5 minutes to 60 minutes and do a fit for that and do a separate fit for everything above that. But in my world, this is pretty good through that. And really, by not having to interpolate, we're already winning a bunch of things through that. All right, that's all I got. That's the main gist of how to run through it through there. Again, I guess the next question is wondering how much change there is if you move 10 miles across the county. Is there a big enough change to really pull a whole new set of data set and recalculate all these, or is it going to be fine? So, all right, thanks.